The combined gas law is an equation that combines both Boyle's law and Charles's law. As a reminder of what we previously talked about here, Boyle's law is the inverse relationship between pressure and volume of gas. So if pressure increases, the volume is going to decrease for that gas. And one of the things that's held constant is temperature for Boyle's law, and the other condition that must be held constant is the amount of gas. Meanwhile, for Charles's law, that's the relationship between temperature and volume. And in Charles's law, that is a proportional relationship. So when one variable increases, the other one increases as well. Or conversely, when one decreases, so does the other. So for example, if temperature decreases for a gas, then the volume of that gas will also decrease. If temperature increased, then the volume of that gas would also increase. With Charles's law, it's the amount of gas as well as the pressure that is being held constant. Okay. Now, the reason why the combined gas law exists is because it's often difficult to hold any of the variables constant when you're trying to do experiments. Okay, so typically when there is a change in pressure, volume, and temperature, we're going to be using the combined gas law, which is going to be this law right here. So P1 V1 divided by T1 is equal to P2 times V2 divided by T2. So, as a reminder here, Boyle's law was P1 V1 is equal to P2 V2. And as we've just said, the amount and temperature is being held constant for Boyle's law. Okay, now since this equation doesn't have moles in it, or N, then we only really have to worry about temperature. And if you hold temperature constant, then that means you can cancel out T1 and T2 since they're the same value. Okay, and if you do that, we get Boyle's law. Meanwhile, for Charles's law, pressure and amount is held constant, but once again, moles aren't in the combined gas law. So if we cancel out P1 and P2, since it's being held constant, which means they're the exact same value, then that's how you get Charles's law. Now, we did have a different version of Charles's law, which was the V1 T2 is equal to V2 times T1, but either one of these forms works. Okay, so you know that you're going to have to use combined gas law when there's been a change in pressure, temperature, as well as volume. Okay, whereas if the question only talks about pressure and volume, you use Boyle's law. If the question only talks about volume and temperature, then you'd use Charles's law. Okay, one way to help you kind of distinguish Boyle's law from Charles's law is I like to think of Charles's law, or just remind myself with the mnemonic device or memory device of Charles likes to watch TV. So T being temperature, V being volume. Okay. But let's take a look at this first example here. So we have a sample of gas at 20 degrees Celsius and 100 kilopascals that occupies a volume of 7.50 liters. Okay, so all of these numbers are connected. They're talking about the initial conditions of some sample of gas. So I'm going to put these all as P1, V1, and T1. And I'm just going to go right ahead and convert the temperature to Kelvin. So that's going to give us 293.15. All right. Now, it says, to what volume will this gas expand if the temperature is lowered to negative 36 degrees and the pressure is reduced to 28 kilopascals? So, for example, a situation where this would happen is if like a weather balloon is rising up, let's say 10 kilometers. So the further or the higher up it goes, the colder the gas is going to get because the lower the temperature. So P2, V2, T2. Okay, so we don't know the volume, but we know that the temperature is negative 36 degrees. Add 273.15 to that. And that's going to give us 237.15 Kelvin. And then for pressure, it was 28 kilopascals. So for the combined gas law, you're going to want to make sure that all of your units are the same. So both pressure values have the same units. So both of ours are in kilopascals, so that's good. And both our temperature values are in Kelvin. That's good. And I don't need to worry about the volumes because we only have one value given for volume. So I'm going to start off by writing this equation. P1 V1 divided by T1 is equal to P2 V2 divided by T2. So since we're looking for V2, I'm going to put a circle around that. And what I'm going to do, ultimately it doesn't matter where you start for rearranging the equation. You could either start by getting P2 over to the left-hand side or T2. I'm just going to start by getting T2 over first because I find that fractions often intimidate students. So I'm going to get rid of the fraction on the right-hand side first. So I noticed that mathematically what T2 is doing to V2 is it is dividing into V2. So I'm going to do the opposite, which is multiplying. So T2, and what you do to one side, you got to do to the other side. So then that gives us T2 P1 V1 divided by T1 is equal to P2 times V2. Okay, and now we're still isolating for V2, so P2 is multiplying V2, so I do the opposite, which is division. Okay, and then I'm just going to go P2 like that. So these cancel out, and then if I write this all nice, neat, and pretty, this will give us T2 multiplied by P1 multiplied by V1 divided by T1 divided by, or T1 times by P2 is equal to V2. All right, so let's plug in all the values that we have. So T2, that was the 237.15 Kelvin. P1 was 100. And then V1 was 7.50. Divided by T1 was 293. So I'm writing out the units so that I can show you guys how the units cancel out. And then P2 is 28 kilopascals. All right, so Kelvin is in the numerator and denominator, so those cancel out. Same with kilopascals. And so we know now that our units will be in liters. So if I multiply everything in the top and then divide by the product of the two values in the denominator, what I'm going to get is 21.6688, number keeps on going on forever, liters. Okay, so if I look at our question here, the value that has the least amount of significant digits, or however many sig digs we should go to, is 2 because of this 28 kilopascals as well as the negative 36 degrees Celsius. So that's going to mean that my cutoff line is right on the decimal. So this is 22 liters for our final answer. Now for the next question, what happens to the volume of a 250 liter container if it has a pressure, or if its pressure tripled and its Kelvin temperature has doubled? Okay, so this one is a bit more theoretical here. So I'm going to start out with my list of givens. And the only real number that it's given us is this 250 liters. Okay, and it's asking us, okay, what happens to the volume of A? So we're asked to figure out, okay, what is V2? What's volume doing? Okay, so to make our life easy, it says pressure is tripled. So I'm going to go, let's say pressure 1 is 1 kilopascal. So if pressure has tripled, then triple of 1 kilopascal is going to be 3 kilopascals. Okay, and now for temperature, I'm going to do same sort of idea. So temperature is doubled, so I'm just going to choose 1 Kelvin just to make my life easy. You could choose 2 Kelvin, 3 Kelvin. All you need to do is times the number by 2 because the temperature is doubling. So since I've chosen 1 Kelvin, 1 times 2, that's going to be 2 Kelvin for my final temperature. So now what I'm going to do, I'm going to write out my formula. And then we're isolating for V2. Now, since I've already shown you guys how to isolate for V2, I'm just going to skip straight to this step. So V2 is equal to T2 P1 V1 divided by T1 P2. All right, so let's plug in our numbers here. So T2, that was 2 Kelvin. Oop. Okay, and then P1, that was 1 kilopascal. V1, that was 250, divided by T1, so that was 1 Kelvin, times by P2, which was 3 kilopascals. So Kelvin and kilopascals, those cancel out. So if I multiply everything in the numerator and then multiply everything in the denominator and then divide the two numbers, what I'm going to get is 166.66 liters. Now for significant digits, with the only number I'm given, which is 250, that's 3 sig digs. So then counting from the left, 1, 2, 3, there's my cutoff line. So final answer, 167 liters is our final volume. All right. Example number 3, we have a bottle containing 560 milliliters of hydrogen gas, and it expands to 1.20 liters. Its initial pressure was 1 atmosphere, and the final pressure was 1.118 atmosphere. If the original temperature was 25 degrees Celsius, what was the final temperature? Okay, so each sentence kind of organizes together what's happening with volume, and then pressure, and then temperature. Okay, so rereading that first sentence there, after I get down my variables. So it says a bottle containing 560 milliliters is expanded to 1.20 liters. Okay, so we start off with this much hydrogen gas, and it expands to 1.20 liters. So the initial volume, that's 560 milliliters, and then the final volume is 1.20 liters. But you see the problem here where where volume does not have the same units. So you can either choose to convert one of your volumes to liters or one of your volumes to milliliters. Doesn't really matter what way you do it. I'm just gonna arbitrarily choose to change this volume into liters. Okay, so there's 1,000 milliliters in a liter, which means we divide by 1,000. Another way that you can know how to convert is you can do the metric conversion scale. So the metric conversion scale is this thing. Okay, so remember, base units are the units that don't have any prefixes to them. So if I look, okay, we're starting off with milliliters, we want to get to liters. So liters is a base unit, milliliters will be found here. So in order to get from milliliters to liters, I'd need to go or move my decimal 1, 2, 3 over to the left. Okay, which does the exact same thing as dividing by 1,000. So 1, 2, 3 to the left, that's going to give us 0.560 liters. Okay, now moving on to pressure. So initial pressure, 1 atmosphere. Final pressure, 1.118 atmosphere. Original temperature, so T1, that's going to be 25 degrees Celsius, which I'm going to work on converting that into Kelvin. So that's going to be 298.15 Kelvin. And then we're looking for the final temperature. All right. So since we have everything, I'm just going to get my formula done. And we can keep on keeping on. Okay, so this time around, we're looking for T2. Oftentimes, when the unknown variable is in the denominator, that kind of wigs students out a little bit. But we'll just chip away at it to get T2 by itself. So I'm noticing that T2 is dividing into P2 and V2. So I got to do the opposite, which is multiplying both sides by T2. This seems a bit counterintuitive, but what we want to do is not only do we want to get T2 by itself, we also need it to be up in the numerator as well. Okay, so that's why I'm doing what I'm doing. So T2 times P1 V1 divided by T1 is equal to P2 V2. All right, so we're still working on isolating T2. Okay, but what I'm noticing here is T1 is dividing into T2, P1, and V1. So I'm just going to multiply both sides by T1. So we get T2, P1, V1 is equal to P2, V2, T1. Okay, now I also notice that P1 and V1 are both multiplying T2. So I got to do the opposite, which is dividing. P1, V1, P1, V1. So T2 is equal to P2, V2, T1 divided by P1, V1. Now that we have our formula, we can start plugging in all our numbers here. So P2, that was at 1.118 atmosphere. V2, 1.20 liters. T1 was 298.15 Kelvin divided by 1 atmosphere. And 0.560 liters. Okay, so if I multiply everything in the numerator and then multiply everything in the denominator and then divide those two numbers, what I'm going to get is 714.2822, number keeps on going on, Kelvin. Now, how the units are working out is atmospheres in the top and the bottom, so they cancel out. Same with liters. This is why we're left with kelvins, because it's the only units that didn't cancel out. Now, the question specifically asks, what was the final temperature in degrees Celsius? So we're not done just yet. What we need to do now is we need to subtract 273.15 to convert from Kelvin into degrees Celsius. So when we subtract 273.15, 441.1322, number keeps on going on. So this is degrees Celsius. Okay. Now, looking at my given numbers, the least amount of sigdigs that we're given is 3 sigdigs. So final answer needs to be in 3 sigdigs. So counting from the left, 1, 2, 3. There's my cutoff line. So my final answer is going to be 441 degrees Celsius.